So I've just given a talk about Flink and sort of what it's for, what it does, how it does it, and now we're going to go over the connector ecosystem. So my name is Danny Cranmer. I am a Apache Flink committer and PMC member and a principal engineer at Amazon Web Services on the managed service for Apache Flink team. So nice to meet you. So we're going to go through Flink connectors. So let's start basic again. What is a connector? So a Flink job is a data analytics pipeline, which is processing data, right? So that data has to come from somewhere, and we have to send it somewhere, want to send the results somewhere. So a connector in Flink is a source or a sink. So a source obviously consumes data from various destinations or integrations, and the sink sends data, the results downstream. So Flink has a wide ecosystem of connectors. I've dumped a bunch of icons onto the screen here. These are not all active. These are not all maintained by the Apache Flink community. So actually the ones that are shown here, these are part of the Flink project. So these are officially supported by the Apache community. And they're released as part of, like, underneath the Flink umbrella. And then the additional ones down here are just some other third-party libraries. So some of them are Apache libraries, like the Hoodie and the Iceberg integrations are managed by the Apache community for them projects, and others are just like self-shipped by vendors, etc. But the point I'm trying to put across here is there are a lot of connectors, and you can add your own. So if what you need isn't on here, you can always add it. Or you can use some other protocol like JDBC, obviously spawns out to a whole bunch of integrations from JDBC. So when we talk about connectors, there are two connector packaging. If you look in Maven Central, you'll see, for example, with Kafka, you'll see a Flink connector Kafka and a Flink SQL connector Kafka. And I just want to talk about this because I think this is maybe a bad naming decision, because when people look at this, they think the SQL connector is for SQL, when actually it's not. It's an Uber jar. So the connector Kafka is not an Uber jar, so it's a jar that's built with just the connector classes. And the SQL connector is an Uber jar, and it bundles in all its dependencies. And this was originally used for the SQL client, which is likely where the name came from. So just to say, if you need an Uber jar of a connector, so if you're working with Python or you're working with a SQL client, then you can use the SQL connector. And if you're using Java, you would typically use the non-bundled one, and you would then create your own Uber jar. As I was just saying, if you're using Java, this is how your job would look like. So your jar would look. So you implement your user classes. When you build the jar, you bundle your classes in there. You also bundle your dependencies. So this could be any dependencies you want to bring in. And you also bundle in the connector classes. We typically use people typically use the Maven Shade plugin for this if you're using Maven. And that result would be an Uber jar containing your code, your connector code, and all the dependencies. When we run on a client, we don't typically build a jar. I'll say when we run on a client, I mean when we run on the SQL client or the PyFlink client, we don't typically generate an Uber jar. So in this case, we rely on these Uber jars that you can download and use off the shelf. And we typically one way we can do it is to have them on a file in our file system. So maybe like a connectors folder. And then when we run up the SQL client, we can point it at this folder. And likewise with PyFlink. And then they would be loaded into the Flink cluster within this job's class loader, and they would be available to that job. And then the final option, which is not generally recommended, is to bundle them into the lib folder of the task manager or the job manager. The reason it's not recommended is because they end up on the parent class loader. So Flink has this parent class loader, and then each job gets its own isolated class loader. And parent class loader, if you put classes on there, it means that if a job wants to use a different version of that dependency for some reason, you can end up with class path issues. And so it's generally recommended to avoid this, but it is possible to do. So now we've covered like the connector ecosystem and how you use them. We're going to go through sort of how they work in case you want to implement your own connectors or you're just interested in how they work under the hood. So for this, we're going to look at the Kafka connector as a use case, as a standard typical connector. So on the diagram here, we can see we have a job manager and we have two task managers. So this example is using the I guess it's not new anymore, Flip27 source API, which, I mean, since I've been using Flink, we call it the new source API, but that was 4 years ago, so it's not new anymore. It's the source API. And the way this works is we have a source coordinator. So we have a coordinator that is responsible for overseeing all of the source consumption. This source coordinator runs on the job manager. And then on each task manager, we have a source reader, which is one per subtask. So if you have 3 parallelism, like we see here, we'll have 3 source readers. And so that's the setup. So the way it works is the coordinator will enumerate splits. So a split is Flink's way of breaking down the source into consumable units. So in Kafka, we have partitions, and each partition is a split. In Kinesis, we have shards, and each shard is a split. If we're reading files from S3, then a file would be a split. So the split enumerator basically would say like list files, list partitions, list topics, and it would identify what there is available to consume, and then it would distribute them across the source readers, and it would say source reader or split reader A, can you please read from partition 1 and 2, and then B, read from 3, and C, read from 4. And the split enumerator would also run continuously. So you may dynamically scale up, scale down, like new files appear in S3, new shards appear in Kinesis. So it would discover them and it can redistribute. And you can implement your own logic here if you want to rebalance things. It's quite a flexible API. Obviously, the Kafka connector, this is all implemented for you. You just use it. You don't need to worry about this. So the split reader reads records, and then we have a record emitter, which will run your deserializer. So you typically supply an object that would deserialize your records from the bytes on the wire to your object representation, which could be JSON representation or CSV. Convert it into Java objects. And then it would output it to downstream operators. There are some other things that happen in here, like watermark, injection, and etc. But I won't cover that now. Okay, syncs. So syncs are somewhat simpler. So the job of a sync is to write data to an external destination. So we're currently at sync v2 API now, which is called, the class is called sync. And if you want to implement a sync, you need to create a sync writer, and there are 3 main methods. The write method is where a record is passed to your sync from the upstream job graph, and then a flush method is to write it to the external destination. And then you have a close, which is called on stop. This is obviously optional. So as a simple sync, you could simply well, it's up to you. You implement them 3 methods and you do what you want. And then Flink calls them as needed by the job. So the next one we have is a stateful sync writer. So if you need state, so for example, when Flink takes a checkpoint, you might want to store some intermediate results or some queued, like buffered records into state so that when you restart your job, you still have that data available. Then you implement the stateful sync interface, and you have an additional method called snapshot state, which Flink invokes, and then you basically use a simple version serializer to serialize your state. And then the more complex one is a 2-phase commit. So Flink supports exactly once processing semantics. And if you want end-to-end exactly once processing, which means you want exactly once delivery to your sync, then you need to implement a 2-phase commit sync. So what this means is that the way it works is Flink has checkpoints, and checkpoints are started and completed on an interval. During this checkpoint, records are, at the start of processing, you would say open a transaction, for example. During the checkpoint, or during the processing time, you would write into this transaction, and then when the checkpoint is complete, you would close this transaction. The transaction close needs to be idempotent for reasons I won't go into now. But the point is that Flink allows you to achieve exactly what delivery guarantees if you conform to the two-phase commit protocol. And then finally, async sync. So async sync is a high level of abstraction. Essentially, when you write a sync, we typically actually do batch internally, because if I'm writing to, say, Kinesis, and I want to invoke put record on every single object that comes through, that's going to be a lot of network overhead. So what we tend to do is we tend to batch up these records and write them when the batch trigger, or when some threshold gets exceeded. So we may say wait for 50 records and then batch them, or wait for 1 second. And we realized that there are the same patterns were appearing in multiple implementations. So we tried to make a generic implementation that will do all this for you. So the async sync is as I said, it's an abstraction over the other bits. It has a concept of an internal buffer, a flush trigger. So the trigger can be time, size, number of records, and it will manage the batching, the buffering, the writing. You can have multiple requests in parallel, and it will handle all that for you. So it's a high level abstraction. It takes away some of them underlying bits if you want to implement your own sync. And it's also stateful. So when Flink takes the checkpoint, if there are any buffered records, it will just write them into the state to make the shutdown time as quick as possible. And then finally, a few slides on lessons learned over the years working with implementing syncs. So one of them is metrics. So in Flink, metrics are very easy to add, and they're very powerful. And we've had cases where we've implemented something, and then there's a problem, and we're like, why is there a problem? And we lack the visibility we need. This is one example. So we added a new Kinesis stream sync in Flink 1.15, and we did all our testing. It was great. And then we found when it went live and people started using it, there were some regressions in performance compared to the old sync. It was an edge case, by the way. It wasn't every implementation, so every use case. And we found that, obviously you can see here, the throughput for the legacy one is a lot faster than the new one. And it turned out that our rate limiting strategy we were using had some inefficient configuration on our the configuration of when to slow down and speed up. So the point is, if we would have put in a metric on the size of our internal buffers, we would have seen that easily. So the lesson learned is add metrics liberally. They're reasonably cheap in Flink, and they're easy to add, so use them. The next point is that graceful shutdown is difficult. Sync or connectors are usually multi-threaded, so they spawn additional threads, and Flink requires you to shut down gracefully. This is just a few instances of issues that have happened with various connectors which haven't shut down gracefully under certain edge conditions that lead to a job failing. So the lesson here is, don't underestimate graceful shutdown, especially in multi-threaded scenarios. Make sure that everything exits gracefully and shuts down and cleans up after itself. And I think finally is skew. So one thing that the connectors need to do is, so for example, in Kinesis, we have shards. We consume from shards, say we may consume from 10 shards. If we have 2 subtasks consuming from them shards, we would expect each subtask to take 5 shards, so evenly distributed. The original implementation of the shard assigner, actually it's still the default, so if you're using Kinesis, please watch out for this. It wasn't linear, or uniform, so it wouldn't necessarily distribute evenly. So if you wouldn't distribute 5 and 5, it might distribute 7 and 3, or 6 and 4, for example, which has caused loads of hot task problems. You know, like this subtask is consuming 10 times more data than this task, There now is a uniform shard signer for the Kinesis source, which is not on by default, so please do use that if you are using the Kinesis source. And that is my time. Thank you.